So question 7 is asking about the catalytic triad that is used in a lot of the active sites of enzymes to catalyze the hydrolysis of esters, amides, and thioester bonds. So specifically serine proteases these are present in their active site. So we will review the catalytic triad in this reaction here where it hydrolyzes an amide bond. So we'll kind of go through it step by step. So I'll start here. Hopefully this isn't too blurry. So the first step that occurs is this hydrogen bonding occurring between this aspartic acid and the histidine here. So overall, the aspartic acid will stabilize this histidine more, which therefore increases its pKa of the histidine. So the next step in this mechanism is a general base catalysis using histidine. So histidine, this lone pair on the nitrogen, will attack this proton here on the hydroxy group of the serine, which will create a very short-lived nucleophilic oxygen that will end up attacking this carbonyl group. And once that happens, it creates a tetrahedral alkoxide intermediate here, which very quickly collapses, as we see here, and in the meantime will cleave this amide bond and we'll get a release of an amine. After our amine is cleaved off, we are left with our serine bound here to the substrate. And the next thing that happens is another base catalysis, but this is a specific base catalysis using water. So our histidine here will grab that proton from the water, where the oxygen will act as a nucleophile then and attack this carbonyl group, again forming an alkoxy intermediate, which again collapses on each other to release this serine on its own. Once the serine is released, we are left with this carboxylic acid group on our substrate. This hydrogen is removed in solution and we are left with this negatively charged acid here as a substrate. So this is the overall how the catalytic triad works in terms of a amide cleavage to release an amine. So next we are asked about the oxyanion hole, which is essentially made up of the backbones of two amino acids, usually the serine and another amino acid that's in the active site hole. So when the substrate, the carbonyl group of the substrate, is near these two backbones, they will act as a stabilization. So essentially when we had done our base catalysis, the general and the specific, we made these alkoxide intermediates with our negatively charged oxygen here. So the backbones of these two amino acids will hydrogen bond with this oxygen here to stabilize it overall. So they're just used to stabilize the intermediate from our tetrahedral intermediate in both spots from the mechanism that we just saw. So next we were asked, what are the main ways in which enzyme activity is regulated? So number one would be the amount of enzyme available, obviously. So this is dependent on the amount of enzyme being synthesized and the amount of enzyme being degraded as well. Number two is allosteric modulation, which we will discuss further in the next question. So I'll skip that for now. Number three is reversible covalent modifications. We discussed this in an earlier question as well, but essentially any modifications like phosphorylation, methylation, glycosylation, any of those that we kind of discussed, those are also very important. Number four would be activation through proteolytic cleavage. We kind of talked about that with the zymogen being cleaved and activated to become an enzyme. So that's the proteolytic cleavage here to activate a new enzyme. So that's obviously extremely important for enzyme activity. Question 9 reads, what is allosterism? Provide a specific example of allosteric regulation of an enzyme and explain how allostery impacts enzyme activity. So essentially, any species that can bind to an enzyme in a spot other than the enzyme substrate active site can be an allosteric modulator. So this can either have an inhibitory effect or a stimulatory effect. And a good example of this is something I believe you went over in class with the ATCase enzyme that produces this N-carbamoyl aspartate, which is very important in terms of pyrimidine biosynthesis. So we know that with the ATCase, it can be activated with ATP, but it can also be inhibited with CTP. So in this case, this is a really good example of allosteric regulation, because this product can either be stimulated using this ATP if it binds, so we'll get more product forming, but if CTP binds, we won't get this reaction occurring. So this is a good example of how it is inhibitory and stimulatory. Question 10 gives us some data for an enzyme catalyzed reaction in the presence and absence of an unknown inhibitor, and it's asking us to find what type of inhibitor using a line mover Burke plot. So you can on your own time try this out, and if you want to pause the video right now and try it yourself, and then we can take it up. But I'll just show you what we have here as the answer. So after finding your 1 over substrate concentration and your 1 over velocity, you should get trend lines that look like this and equations that resemble that. So when you're trying to find which inhibitor you may have, the first thing you want to do is remind yourself of the Km and Vmax equations. So we know that the y-intercept equals 1 over Vmax, and our slope is going to equal Km over Vmax. There are a few more equations for this, but we'll leave those two for now. So with this, we can tell immediately that with these two equations, the y-intercepts are the exact same. So when we look at our equation for Vmax, the y-intercept equals 1 over Vmax, we know that the Vmax for each of these are the exact same. And from previous questions, we know that the change with the uninhibited and inhibited reactions will still have the same Vmax in a competitive inhibitor. So we know that this will be a competitive inhibitor. Now if we go back to the original question, 10b asks, does the inhibitor X combine with the enzyme substrate, or with both? So if we remind ourselves about competitive inhibition again, we have our enzyme and we have one binding site, which the inhibitor will bind to, and the substrate won't bind. So the inhibitor will bind with the enzyme, not with the enzyme substrate complex. That only occurs in uncompetitive or mixed inhibition. So next, we are asked to calculate the Ki for the inhibitor, assuming the final concentration is 0.2 millimolar. So get rid of this and move this down. So we know that the Km for a competitive inhibitor is affected by the alpha factor. And the equation for alpha is 1 plus the concentration of inhibitor over Ki, which is what we're looking for here. So we also know that alpha you can calculate by getting the fraction of the slopes. All right, so if we take our first slope from our line mover Burke plot, 0.0533 divided by 0.0266, we will get a value approximately 2. Okay, you can also do this with exact values, but I will just approximate for now. So if we take this equation here and rearrange it, we will get Ki equals inhibitor concentration over alpha minus 1. All right, so when we input our values here, we will get 0.2 millimolar over 2 minus 1, where our final amount will be 0.2 millimolar as well, right? Question 11 asks us to draw a sketch of the velocity as a function of substrate concentration curves, so Michaelis-Menten curves for each situation. I've already drawn the uninhibited versions of each enzyme here. So we'll now do, for A, it's asking for the competitively inhibited enzyme. So competitive enzyme, we know that our Km will increase and then our Vmax will stay the same. So eventually at a very high concentration of substrate, the Vmax will stay the same as the original, but our Km will increase. Okay. For B, we have a uncompetitively inhibited enzyme in the same plot. So how we do this, it would look something along the lines of that, where both our Vmax and our Km are decreasing.